Okay, so chapter 3.2, we'll be talking about measure of variability. So in chapter 3.1, we talked about measure of the central tendency. So when you have a data set, how you will find the characteristics of data set. And the first thing that we would look at it is where the center of the data set. But sometimes the center of the data set, the central tendency measure is not enough to describe the data set fully. So for example, if you see the data set 1 and data set 2 here, the data set 1 has 1, 2, 3, 4, 5 as a data point, and data set 2 has 2, 3, 3, 3, 4. So if you draw a histogram, you can kind of see how the data set 1 and data set 2 would look like. If you're using central tendency measure here, fortunately for these cases, both of these data sets are symmetric. So it really doesn't matter whether you would use mean, median, or even mode is a little different, but mean or median really doesn't matter. Let's just stick with the mean. So if you calculate the mean of the data set 1, that will be 3 in the middle. Data set 2, again, your mean will be 3. So if you're just using central tendency measure, you would say, well, data set 1 has the center at 3, data set has a center at 3, they are the same data. But is that actually true? If they're not really exactly same, how would you describe that these two data sets are a little different? So one of the easiest way to describe probably for the difference between these two data sets is even though their center is the same, that'd be fair to say that the data set 1 is more spread out all over the place, and data set 2 is a little bit more centered. There are more values in the center and other values are actually close to center. Okay, so that'd be fair to say that data set is more spread out and data set 2 is more centered. That's what we call the variability or dispersion. So you would say data set 1 has more dispersion or more variability, and data set 2 will have smaller dispersion compared to data set 1 and smaller variability. So to make a long story short, the central tendency measure with variability measure will actually be really helpful to describe the data set. So we'll talk a little bit more about the measures that we can use to decide to measure how spread the data set is. Okay, there are 3 big measures that our textbook was talking about. One is range. The other one is sample variance, and another one is sample standard deviation. Sample variance and sample standard deviation are very closely related, and we're gonna get that point in a little bit. The range is a little different. It is a very simple measure. You're just taking the largest value minus the smallest value, and then you see what's the range of the data. So if we go back to our data set 1, your range will be 5 minus 1, which is 4. Data set 2, your range will be 4 minus 2, 4 maximum, 2 minimum, so it will be 2. So you would say for the data set, for data set 1, the range is 4, and data set 2, your range is 2. So you would say something like data set 1 has a bigger range than data set 2, thus more spread out. Very simple, easy to calculate, a simple calculation. That's the advantage of using range, but at the same time, you can imagine that it only uses the data set that is minimum and maximum and really doesn't care what's happening in the middle. So the quick measure, but it's not really a comprehensive measure. So more common ones to use is sample variance and sample standard deviation. So sample variance, I mean, we're going to talk about where this formula coming from in a little bit, but I want you to actually look at the formula first here, and then let's just try to understand it a little bit. For there's this summation, which means you're going to add all up, and you see that x minus x bar here. X bar is your mean still. So you're kind of doing calculating x. X is each data point. This is each data point. And you would see how each data point is far away from your x bar. And from that distance, you take a square and you add all up and divide it by n minus 1. The second formula is actually mathematically exactly same formula. You can actually prove that's actually exactly the same formula, which I'm not going to ask you to do it. When you're doing a lot of hand calculation, the second formula is actually relatively easier to do it, but we're going to actually use the calculation, the technology for actual calculation a lot more than hand calculation. So we'll probably focus on this first formula for this time. Sample standard deviation is very similar measure. It is just you calculate the variance there, and then you take a square root of it. So one of the advantage of using sample variance is just that if you're starting from a unit of feet or gram or whatever, once you take the square of it, calculating variance, your measure of unit of your variance became square feet. But taking a square root of it, you're going back to your original measure unit. So we'll be going back to feet, for example. So some people actually like to use it a little better. But when you're using variance or standard deviation to compare between data set and which one is more spread out, you're always going to end up same results. Really doesn't matter which one you would use. Okay, so then let's quickly talk about where this variance is coming from. So we call it motivation of data set. And again, what we're trying to do in this section is how spread your data set is from the center. Okay, so if you look at the data set 1, I'm going to draw a simple dot plot. So here's 1, 2, 3, 4, 5. I'm going to do the exactly same thing for the data set 2. 1, 2, 3, 4, and 5. Okay, so your center is 3 right here. And same thing here, your center is 3. Again, we're measuring how far your data set from the center. So you can see that the data point 1, so here's your data point 1, 1, 1, 1, 1. I guess I should have done this before. Here, because there are 3 data points and then 4 points. This point 1 is this much far away from the center. This one, this much far away from the center. This one, this much far away, this much far away, right? So for the data set 1, you can say that, well, this one is 2 and 1 and 1 and 2, right? So you can say this one is 2 plus 1 plus, and the 3 is exactly in the center. So this much distance that you can actually get it from the data set 1. But just to be fair, because if you have more data set, data points, that you're going to actually end up a bigger number here. So to be fair, we should probably take the average of it. Okay, so for the data set 1, this one will be 6 over 5, right? Which is 1.2. And the second one, you can say, well, this one is this much, and the data point 4 is this much. So 1 and 1. So in a way, you can calculate 1 plus 0 plus 0 plus 0 plus 1 divided by 5, which is 2 over 5, which is 0.4. Okay. So this is one measure that actually you can use to compare the dispersion of the two data set. 1.2 is larger than 0.4. So the data set 1 with the 1.2 it is more spread out. It is your data set is far away from the center compared to data set 2. Okay. I'm gonna just hang up my phone and I'm gonna move on. So what we actually did here, you can kind of formulate it. So what this one is, we call that average distance. What you did is you take the each data point and subtract your sample mean, right? So you did 1 minus 3, right? And then you kind of add up. But when we do that, we need to be a little bit careful because if you do the 1 minus 3, that will be actually -2, not exactly 2. And if you, the same way, if you do the 2 minus 3, will be -1. So if you actually use this guy's trait, the x minus x bar and then add up, you will always actually end up 0 just by the definition of x bar, the sample mean. So we cannot really use that measure itself to tell the to measure the distances. So one of the way we did actually is let's take the absolute value of it and divide by n, and that is just called average distance. And it's a fine measure to use it, but it's not really common, partially because this absolute value is actually hard to deal with. So we're going to use another way of doing it, doing all the this x minus x bar value to be positive. Rather than absolute value, we're going to use the square. Hold on. I don't know what I did. Instead of absolute value, we're going to use square and sum, right? And we're going to do divided by n minus 1 rather than n. And this guy is where the sample variance coming from. So sample variance, we call that S square, and we're gonna actually use that. So that's where the variance is coming from. Oops, not that one. Okay. Okay, so you can. No, not that one. So here, we're gonna actually look at how we can calculate this thing when we actually have a data set in a spreadsheet. We're gonna quickly calculate the data set 1, variance of the data set 1 by hand, and we're gonna actually move to a Google Sheet, and so that, you know, when you have a bigger data set or more complicated data set or whatsoever, then you can actually use the Google Sheet a little bit more easily. So as you can see in this table, your X is again your data set 1, 2, 3, 4, 5. And in the second column, what we're going to do is we're going to calculate X minus X bar. So here X bar is equal to 3, right? So that was the central tendency measure there. 1 minus 3 is -2. 2 minus 3, -1. 3 minus 3, 4 minus 3, 5 minus 3. And again, if you add all this up by the definition of X bar, because X bar is in the center of the data set, if you add all those differences, you'll actually end up having 0. That's whatever the data set you're using, you're going to have that. And then you're going to take a square of it. So here, 4, 1, 0, 1, 4. So if you add all that up, will be 10. Okay. then your S square is, for the data set 1, we're going to have this guy is actually same as this guy, right? This guy is that guy. Okay, so we're going to have 10 over n is sample size, right? This guy is sample size. So here sample size is 5, right? We have the 5 data point. So we're going to have 4 here. So you're going to have 2.5 there. Okay, so that's how you can actually use the calculation here. Okay, so what are we going to do? Here is we're going to go Google Sheet. So I mean, you can make your own Google Sheet as well. Hold on a second. But if you go to your Blackboard and click Start here, all kind of useful information there. There's a category called Class Google Sheets. So if you click that, there's a lot of different tabs that we're going to use throughout the semester, because we're going to actually use quite a bit of Google Sheets. So let's click that. I'm going to take you there, and we're going to actually play with the variance tab. Do you see that there's a lot of different tabs at the bottom? And you know, we'll use it more later, but today we're going to use the tab called variance, and this one should look pretty familiar, right? So here's the x and the 1 2 3 4 5 there, and then how we're going to do is x minus mean of x bar, x mean of x there, so x bar there. So you're just going to click there, and is equal to x bar, the x minus the mean of the average of these guys. And if it's not actually perfect, and you'll see in a second. So when you do that, this one will actually not do it, because instead of instead of doing that, you want to actually stick with A2, A6 for all the time. So you're going to actually put the $ over there, so that when you calculate the average of A2, A6 throughout for all the rows, it will stick with those rows. So if you do that, and then drag it, and now you're going to see -2, -1, 0, and 1, 2, like before. And again, if you want to check what's the sum of these 5 numbers, again, it will be always equal to 0. And the next column, we want to do square it. So this one will be just square. This will be 2. And we'll automatically do that. And then your variance will be just equal to sum of these values divided by the count. So that's the n. So the count function is just count how many data point is there, minus 1. Don't forget the -1 there. And there is your 2.5. Okay, and you have a standard deviation, which is the square root of SQRT, is the function of square root of that guy. So you're going to have your standard deviation of 1.5811. Okay, so once you have that set, you can copy and paste it. I just copied and pasted. How about the data set 2, which we have 2, 3, 3, 3, 4, right? That was our data point. And if you change it, it will automatically pretty much change all those values, but still this one is x minus the mean of G2, G6, right? Okay, right there, which is 3. And then you do the same exact thing, and then there's a variance there and standard deviation there. But if it's how you would calculate the variance, but the more importantly, how we're gonna actually use these values to compare the data set. So the variance and to the variance should be compared to the variance. If you see the variance 2.5 and 0.5, data set 1 has the bigger variance, thus it is more spread out. If you want to compare the standard deviation of the first data set is 1.58 and second data set is 0.707. The standard deviation for the first data set is bigger, thus it's more spread out. Okay, so you can make a comparison of the data set like that. Okay. Couple notes about the notation. So we briefly talked about in the last section that for different measure, depending on you're talking about population parameter or sample statistics, we will be using different notation. The population mean, and when we're talking about mean, your parameter population mean, use the notation Greek letter mu, and statistics, which is sample mean in this case, we'll use notation X bar. For the variance, parameter for population variance will be using sigma square, and sample variance will be S square. Population standard deviation will use sigma, and sample standard deviation will be using S. Notice that your parameter always use Greek letter. So that's what we do typically. Okay, before we move on, let's actually talk a little bit about other technology. So other than Google Sheet, we'll also use something called StatCrunch. They're a little better than Google Sheet if you want to do a little bit more statistical analysis. So, doing the hypothesis test and all that, it's a little better. So we will actually use StatCrunch as well. So we will use the class survey data set, which we played with a little bit in our StatCrunch lab. So you probably got those data set already. So what we're going to do is we're going to go stat key and get the class survey data, and we're going to find the means and the standard deviations for socializing hour for on and off campus students. And then we're going to compare those values. Okay, so we're going to go StatCrunch. And again, if you go back to your Blackboard, again, under the same area, the same place, start here, syllabus and info. There's a StatCrunch. If you click there, it will actually take us to the StatCrunch. There are several different ways that you can get the data set, but assuming that you've done this in the lab, the StatCrunch lab, you already uploaded this data set. Once you have done that, it is actually under My Data. Otherwise, you will just go from a file and on my computer, and you just find where the data set is and get it. So you go My Data, and then here's my data, survey data. And see, there's a whole bunch of data point there. Okay, here we wanna calculate the mean and standard deviation for our what was the one? Socializing, right? So we're gonna actually go to summary stats and just columns. And then we'll be interested in hours of socializing per week. And we want those information summary statistics for on and off campus, right? So on and off campus, on campus group and off campus group. So I'm going to click that one. And then I'm just going to leave all the statistics there. You can actually, add more and delete from some of them if you want. But for now, we're just going to keep it as it is. And if you click compute there, here is all kind of information that you can find. Off campus, there are 115 students answered. They live off campus. 185 students said that they live on campus. At this point, we'll be focused on the mean value and the standard deviation value. So for off-campus, your mean socializing hours per week is about 10.39 hours. On campus, 16.47 hours. And standard deviation will be 7 and 14-ish. Okay. So, and all the other values, I mean, you might actually recognize it, but we're going to just stick with the mean and standard deviation here. So if we go back here, you can say, whoopsie, okay, for the, let me go back and remember off campus, 10 off campus. So off campus, your mean was 10. And on campus, your mean was about 16. Standard deviation was 7 and 14. Okay, I'm going to just 7 and okay. So using this number, the third item was saying compare the socializing hours for on and off campus using mean and standard deviation and how you're going to interpret it. So you can kind of say, looking at, well, on campus students on average spend way more time socializing, but at the same time, their standard deviation is way much bigger, right? So the data set is really dispersed as well. So there's a lot of variation for students who live on campus in terms of socializing hour. Okay, so the next thing that we'll be talking about is empirical rule. Right now, we're actually not justifying these numbers, but chapter 7, you will actually get to see where these numbers are actually coming from. But for now, when you're having the symmetric and mounded shape like that, right, nice bell shape, the 68% of data set is in between mu minus sigma and mu plus sigma. So in between these two numbers, they're about 68%, and 75% of the data set belongs in two standard deviation here and here. Right? And the three standard deviation, 99.7% of data set is in there. And since it is symmetric to the center, you can kind of say that out of 68%, there are 34% here and 34% here. So because it's exactly symmetric. Notice that if you do that, here is your 2.4% here and 0.1% here. And why are we talking about this? Can we actually come up with any example that we can use real life? There is one example I can actually think of. The IQ score is very famously standardized so that the mean is 100 and standard deviation is 15. And if you actually Google search genius, the definition of genius, there are a couple different definitions there. Some website will say 130 or more will be larger than 130 will be defined as genius, and there are other sites as 145 is being genius. So I'm not really trying to argue which one is better definition or anything like that. But since it is very well standardized test, which means that mu is 100 and sigma is 15, and with the bell shape, so you can kind of write down, okay, my mu is 100, mu plus sigma is 115, mu plus 2 sigma is 130, mu plus 3 sigma is 145. So when we are define the genius as 130 or more, you're actually saying that about 2.4 plus 0.1%, which is 2.5% of a population is defined as genius. If you're defining your being genius as 145 or more, you're defining about 0.1% of population belongs in this category, and they're called as a genius. So depending on how you want to define, you can do that. So empirical rule can be used a data set like that. And one of the catches, I mean, which is very, very convenient, but one of the catches, it only works. You have a normal, like a really perfect symmetric bell-shaped. If not, there's other way that you can figure it out, but we're not going to actually worry too much about that. Okay, so it is 3.2. We'll skip 3.3 and we'll come back with 3.4.